Hi students, Professor Nugent here. In this video, we're going to discuss how in the world do you select lag length, that P, to include in your model. How many lags do you include in your model? And we're going to discuss that information criteria is the way to do this. So omitted variable biases are relevant for forecasting. Usually we talk about omitted variables as one of the ways to help us decide what variables to include. But here it's irrelevant for forecasting. So if we want to think about how many lags to include in our model, you could use sequential downward T or F tests. That is including a large number of lags and only excluding the last insignificant lag. But if you do that, models chosen tend to be too large because of the type 1 error. Another better way to determine lag lengths is to use an information criterion. Information criteria trade off bias, which is too few lags, versus variance, which means too many lags. The two information criteria are Bayes information criteria and ECO321 information criteria. And typically both are evaluated and reported in choosing the number of lags to use in a time series model. Let's first look at the Bayes information criterion. The Bayes information criterion is given by this formula next to the big rainbow star. BIC, Bayes information criteria, of P lags is equal to the natural log of the standard, the sum of squared residuals of that model with that many lags over T, that's the number of observations in the time series, plus P plus 1, P is the number of lags plus 1, times natural log of T over T. The first term is always decreasing in P number of lags. So the larger the number of lags, the better fit, because this is always decreasing in P. So larger P, better fit. The second term is always increasing in P, right? So here this is decreasing in P because standard, the sum of squared residuals is decreasing in P. But this one is increasing in P, right? As P goes up, this term goes up. So you have a good trade-off here. So let's talk about the second term. The variance of the forecast due to the estimation error increases with P, right? So you don't know, you're estimating population parameters using sample statistics. So you don't want a forecasting model with too many coefficients because that brings about too much uncertainty. But what is too many? That's a big question. What is too many? So this second term here, that's a penalty for using more parameters. Each parameter that you increase, this second term increases by 1. It increases by a factor of 1 in this term, right? So it increases the forecast variance. Now, minimizing BIC trades off bias and variance to determine a best value of P. So the result of using this information criterion is that the estimated value using BIC converges in probability to the true value of P. So in practice, how do we use this? We would estimate a number of models. We would estimate a model with P equals 1 all the way through, for example, 8, and we would choose the model that has the lowest BIC. Okay? Let's look at the ECO321 information criterion. The ECO321 information criterion is similar to Bayes information criterion. The first term is in fact exactly the same, and the second term we have replaced natural log of T with 2. Okay, the penalty term in the second penalty term, it's smaller for AIC than for BIC because 2 is less than natural log of T. So AIC tends to estimate more lags or larger P than BIC. This might be desirable if you think longer lags might be important. However, the AIC estimator of P isn't consistent. It doesn't have this convergence in probability that BIC does. So it can overestimate P that because the penalty is not big enough. Let's look at an example. Let's look at an example here. So we have the Bayes information criterion and the R squared for autoregressive models of United States GDP growth rates using data from 1962 of quarter 1 through 2016 of quarter 3. In the first column, we have the number of lags, P equals 0, 1, 2, 3, 4, 5, 6. We have the sum of squared residuals over T in the second column, the natural log of that number. In the third column, we have the third that we have in the fourth column we have that second term, that second penalty term. In the fifth column, we have the BIC. And so we're going to look for which lag minimizes BIC, and observe that the lag P equals 2 gives us the smallest BIC, and so we would choose, the BIC chooses 2 lags. Also, observe that if you just used R squared to choose the number of lags, you would always select the largest number of lags. And that's because, R squared always goes up as you add variables. So you're always going to choose the largest number of lags. So we're not going to use R squared to choose how many lags to include. We're going to use information criteria, and we're going to choose the number of lags that minimizes the information criteria. All right, let's generalize this method to multivariate models, which is the autoregressive distributed lag model. If we let K equal the total number of coefficients in the model, including the intercept, the lags of Y, the lags of X, then BIC, the Bayes information criteria, is BIC of K equal to the natural log of the sum of squared residuals over T plus K times natural log of C over T. And we can compute this over all possible combinations of lags of Y and lags of X. This is a lot. There's you could potentially program it. There are ways to program it. In practice, you might choose lags of Y by BIC and decide whether or not to include X using a Granger causality test with a fixed number of lags, and the number depends on the data and application. And recall that we haven't yet discussed the Granger causality test, but we will in a video in the near future.